Okay, I left you hanging with the additional information I'm going to give you. If I remember what I was about to say, okay, well, is that anytime you have a stochastic matrix, the eigenvector, -1, 1 is going to be an eigenvector. They all give you this. Okay, but this one changes. Stable population ratio is different. Like if you change, if you put the 0.9 here and the 0.1 here or whatever, you're switching the conditions, and now you're going to have twice as many diminished as sane to have the stable population. Okay, if you just kind of switch your percents. It just gives you a symmetric vector. So obviously you get a different eigenvector, right? Now if you change the 0.9 to a 0.8 and the 0.8 to a 0.7, you're going to get even a different eigenvector, okay? Now, I'm going to put it this way because we've seen this, and hopefully, and this takes quite a bit of mathematical sophistication to understand the statement that I'm about to make. Of course, then you should question whether I can even make it. Well, I mean, okay. So, takes quite a bit of mathematical sophistication, but I believe you're developing it, and I believe many of you are going to understand this completely, and some are going to have to ponder it a little bit more. Okay? So I'm just going to say the matrix that I'm going to represent by R1 minus S, 1 minus RS, which is one standard way of representing a stochastic 2x2 matrix. Okay? Always has, I'll write it this way, -1, 1. Is an eigenvector. Okay? Though the eigenvalue changes, if R and S change. That means if you wanted to do the 0.7, 0.2, 0.3, 0.8 matrix instead of this one, you would still get this as an eigenvector. So this part of the picture wouldn't change, except that your eigenvalue would change. So, this thing might be a little longer or a little shorter, the W vector here, the vector you get when you multiply by the A. Okay? It's going to make this vector shorter. Always. And you can prove that in terms of R and S. It's not hard if you do the algebra. Okay? The other eigenvalue is always 1. We proved that. First day we saw this, amazing me, you were able to factor that discriminant and you got 2 eigenvectors, okay? And one of them was 1. That R plus S thing matched, between, well, yeah, anyhow, we could write it out. I'm not going to try to allude to it because you probably won't remember all the details. Maybe you do. When you do that factoring on the determinant of what you get up here, if you put the negative lambda in and stuff, okay? That whole thing you did, most of you did the algebra with, and or came very close. You determined that one of the eigenvalues was going to be 1, and that's the one out here that gives us a stable population. Okay? I'll say the associated eigenvector is the S to D ratio for stable population. So right here you have what we could call a theorem about 2 by 2 stochastic matrices in terms of eigenvalues, which you know how to compute, and eigenvectors that I haven't yet showed you how to find, but it's easy. Okay? Once you have the eigenvalue. I don't want to lay too much on you, so I'll save showing you how that works out. Or maybe I'll put it in the problem. All I got to do is give you a simple instruction. Okay? So that's kind of where we are with this. And this is a big deal picture. Okay? This whole idea of eigenvalues, you know, eigenvalues and eigenvectors pretty much run the universe at the quantum mechanical level. Okay? The energy levels in the hydrogen atom, which I've mentioned before, are eigenvalues, correspond to eigenvalues and eigenvectors of matrix equations. Okay? Probability equations for what we call a complex valued probability amplitude. And you don't, you know, quantum mechanics is a fairly advanced physics course in an undergraduate curriculum, and a really, really wonderful but very challenging course at the graduate level. Okay? So it's not something that we're going to work with. I'd love to. If we're here all summer, we probably would do a little bit. Okay? So, knowing what an eigenvector is, at least in this context, gives you a big leg up when you take a linear algebra course, okay? As everybody should. And gives you some idea of how algebra and geometry can work together. And we'll draw more pictures based on this idea, okay? Right now, I just want you to digest the idea, though.